video open somewhere? Sorry. It is certainly live because I can hear myself in YouTube. Okay, thank you so much everybody for coming to this session of 3DGB. Today I have the honor to introduce Shuran Song, who is an assistant professor at Columbia University. Shuran does a lot of really exciting work on robotics and vision. And before that, she was doing also really super cool in 3D vision. So I'm a really big fan and I'm super excited for this talk. We also have wonderful panelists. David Fui from University of Michigan and Deepak Pathak, who is a professor at CMU. They both also work in this area, and so I'm really excited for the chat afterwards. All right, Shuran, please take it away.
Okay, thank you so much for the introduction, and I'm so happy to be here, and I'm really looking forward for the discussion afterwards. Yeah, so today I'm gonna just talk about two of most recent work from our group on deformable objects, perception and manipulation. Okay, so let's get started. Okay, yeah, so we all know that deformable objects or deformable class is really everywhere in our everyday life, right? So every morning, the first few things that you might do after you wake up is probably like making your bed, wipe your face with a towel, putting on your shirt, and then finally put on your mask before you get out of your door, right? So during this process, you're actually effortlessly manipulating all this deformable class even before you really fully wake up. So, however, this kind of similarly trivial task of accurately manipulating deformable class is still an open challenge for today's robotic systems, which are often designed to handle rigid objects with very rigid movements. So a natural question here is what makes deformable class different and therefore preventing us from using the algorithms that we developed for rigid objects, right? So here are a few main reasons. So first is that for deformable objects, they actually often highly underactuated. So what does that mean is that so when the robot is actually holding a piece of cloth, for example, what it can control is only a small region of the cloth that's around its gripper. And the rest of the cloth is just hanging there, and the system actually do not have any direct control for the positions that is out of contact. And the second is that the system also needs to deal with extremely high degree of freedom when they deal with deformable objects. So in contrast to rigid objects where their pose or configuration can be fully specified with a few numbers, a piece of garment or cloth can easily have near infinite degree of freedom. So how to efficiently represent and infer their full configuration is another big challenge. And the third challenge is more specific to cloth, which is a subcategory of all the deformable objects, which is about their geometries. So for objects like cloth or garments, they often consist of very thin 3D geometries that is not watertight. So this kind of unique geometry or like geometric property makes them actually ill-suited for many typical 3D shape representations that are designed for rigid, like solid rigid objects, such as the occupancy grids or sign distance functions. Therefore, really requires us to think about new shape representations that can represent those kind of objects. And finally, because deformable cloths are so thin and they can deform in so many different ways, cloths can also oftentimes experience the most extreme case of self-occlusion. So for example, like in this case, the ratio of the observed surface compared to the full surface of the garment can be as little as 10% in many real-world applications, which make perception and planning tasks extremely difficult because of the ambiguities of the self-occlusion. So due to all these challenges, prior works on garment or cloth perception often build on top of a few simplifying assumptions, such as assuming like high visibility of cloths when the cloth is worn by a human, or rely on very high, strong prior knowledge about the objects, such as their accurate instance level match or full state information in the initial observation, where the problem basically reduced into an instance level tracking problem. So in today's talk, what we want to do is to kind of relax those assumptions just a little bit, and then try to answer the question of how we can effectively or efficiently perceive and interact with a piece of cloth under severe self-occlusions. And that's why we have the title Unfold Unseen. So concretely, I'm going to talk about two projects, one on perception, the other on manipulation. So in the first project, we'll use the category level part of garment in order to infer the unseen part of the cloth. And then in the second project, we will actually use a robot's physical action to really unfold the cloth and reveal the part of the cloth that is not directly visible. Okay, so let's start with the first project, where the goal is trying to do category level post estimation for garments. So this work is done by Cheng Shi, who is a first year PhD student in Columbia. So the task we want to do here is basically post estimation for garments, garments such as like t-shirt, dresses, or pants. Right. So the first question we have is actually how we should define the pose given a piece of garment. So if we take a look on rigid objects, the pose definition is actually quite clear. So given our object instances, their pose or configuration can be basically fully described by 6 degrees of freedom, which consists of 3 degrees of freedom of translation and another 3 degrees of freedom of rotation. And then we can extend this definition for a collection of objects or like a collection of object instances. And we can just in order to do that, we just need to kind of define a shared category level canonical pose. So for example, for cameras, we just need to kind of use the direction of the lens in order to align different object instances, and then use that orientation to define the shared canonical pose for this category. And then the task of category level pose estimation is then defined by inferring the corresponding transformation between the observed object instances to this canonical pose, whereas observed objects now can be something that the algorithm has never seen before. So we call this representation NOX, which stands for normalized object coordinate space, which we'll also use again in this project. So similarly, we can extend this idea of NOX for articulate objects, where we just by adding a few degree freedoms on the articulation. So articulate object is basically can be treated as rigid parts that are linked by revolute or prismatic joints. And the pose for each part can be just basically defined in the same way as a rigid object. But additionally, we also need to estimate the object's joint parameter and also their joint state in order to fully describe the object pose. So in order to do that, what we need to do is to canonicalize all the joint states in order to provide a category level pose definition. Okay, so the question now is how about deformable objects, right? Like t-shirts, how we are going to define their pose? Are we going to specify the pose for every single vertex on the cloth? Well, the short and simple answer is actually yes. Since that a garment has such high degree of freedom, in order to fully specify their configuration or pose, we kind of need to specify every point location on the t-shirt surface. And even more, we actually need to specify the position for both observed and unobserved surface. Since we no longer have the rigid body constraints, therefore we cannot solve the pose for the unobserved surface or unobserved points using algorithms like RANSAC. So obviously it is a lot, and in some sense it's too much for the network to infer all those information. However, since that not all the degree of freedoms are completely independent, therefore there's a very strong constraint or part the algorithm could leverage to simplify this problem. And the key question here that we need to answer in this project is how we can impose those constraints or priors to make this problem solvable. Okay, so again, we actually defined the category level canonical space for different garment categories, such as shirts or dresses. So this canonical space is defined across different garment instances under the same configuration. So here the configuration that we use is defined by the garment geometry worn by a person in a T-pose. So as a result, this shared canonical space actually allows the algorithm to learn a strong priors within each garment category that actually are independent from their configuration. So one way to understand this canonical space is that given a coordinate in this canonical space, it will actually map to the similar surface location on different garment instances, which means that they might or very likely to share similar local geometries and semantic meanings. So for example, in this case, all the 3D points on the shoulder of the t-shirt actually share a similar coordinate in the canonical space. And then later in my slides, you'll probably see a lot of visualizations like this, where the color of the RGB color is actually indicating the canonical coordinate in the canonical space. So when you see the visualization, you can basically imagine that it's mapping to the canonical space. Okay, so in total, in this project, we actually consider 6 garment categories that's provided by the class 3D dataset. And with the post definition, now we can finally define the task. So given a partial observation of an unseen garment, the goal of the algorithm is to map all the observed points into a canonical, into a category level canonical space, like this. And then the next question is, how about those unobserved surfaces? Right. Remember that we no longer can use the rigid body constraints and directly solve the positions for those unobserved points using RANSAC. So what we do is instead we actually ask the network to complete the garment's full 3D geometry in this canonical space, and therefore provide the poses for those unobserved surfaces as well. And finally, we'll need to map this complete 3D shape back to the observation space so that the output is can be directly describing the garment's configuration in the same observation space. So to summarize, the key idea for this project is really try to formulate the deformable object post-estimation task as a shape completion task in the canonical space. And therefore, by mapping the observed points into the canonical space, we can estimate the pose for all the observed points. And then by completing the shape in the canonical space, we therefore estimated the pose for all the unobserved surface. And since the completion happens in the canonical space, the algorithm can actually leverage a much stronger shape pair that are invariant to the object configuration. So next, I'm actually going to talk about how we do that by getting into details of each of the steps. So first is how we can get the info observation. All right, so here we actually less interested about the task of on-body class perception, where the class is actually worn by a person already, since the task is pretty much reduced to human body pose estimation. So instead, what we are more interested is how to estimate the garment under arbitrary configuration. However, if we do not pose any constraints on the configuration, the task can quickly become way too hard and in some cases impossible to solve. So instead, what we do is we will use a simple robot action to transform the class from an arbitrary configuration to a configuration that is a little bit more trackable for perception algorithm. So what we do is basically ask the robot to kind of pick up the garment from any location that it can. And then by using this very simple pickup action, the system is able to reveal more surface area of the garment using the gravity force. And also at the same time, the pickup action itself is actually very simple. Therefore, it does not rely on any prior knowledge about the cloth or its pose, which means that it can be executed robustly with almost 100% of success rate. So after that, the robot will actually take RGBD images of the garment and use that as an input to the algorithm. So after we get the visual observation, the next step is actually to label all the visible surface in the with their canonical coordinate. So we formulate this task as a standard point-wise labeling task by using a standard .NET++ network, where the output is the canonical coordinate prediction for each of the input points. So when we train the network, actually we found that it is much better if we use classification loss by quantizing the canonical space, since it is more effective to model the bimodal distribution caused by the garment symmetries, and also addressing the problem of regressing towards the mean. So later we'll see that it is actually okay for the network to predict incorrect coordinate labels that is mirrored from the ground truth, like predicting the left sleeve to the right. That kind of mistake is actually acceptable, and the algorithm actually able to self-correct those kind of error in the later steps. Okay, so here are some prediction results for the first stage. So we can see that the algorithm is able to infer the canonical coordinates for different garment styles, such as long or short sleeves. I think here is shirts.
Shuran, a quick question. I think I missed this, but how did you get supervision for the point net?
Yeah, so first, because we generate the training data in simulation, so we can actually get the per point label in simulation. So okay. the ground truth is rendered like UV coordinates or like the Knox coordinates, and then we just directly supervise on that.
Okay, thank you.
Okay, any other questions?
So did you write your own simulation algorithms to pick up the clothing?
Yeah, so for this project, actually, we use a Blender. And in the later project, we use another simulation combined with another renderer to do the class. Yeah.
Great, thanks.
And I'll just jump in. You might answer this, so you might have a slide for this later. I'm curious with the front back symmetries, because you're using points. I'm curious about what sorts of signals is it using to? Is there a signal it can use, or is it something pretty subtle in the shape, or is there other things that can serve as all these ambiguities?
Yeah, so actually, there's one symmetry is a left and right symmetry. And so from what we observed, the network actually has a very hard time to distinguish left and right. And but another thing we found is that it's actually okay for them to not able to distinguish left and right, because shape completion actually don't really care, and you're still able to complete the shape. And then the third step actually cares a little bit about the left and right, but because of the way that we formulate this problem, they actually are less sensitive about this the error in that step. Yeah. Okay. So I move forward. Okay, cool. Yeah, so this is another like a result for other categories. So I think on the top is a skirt, and on the bottom is dress. Yeah, so here you basically can see that the red dots are labeled with the grasping point. So the reason we can get the grasping point location in the canonical space is because we know the gripper location in the observed input space. And then by predicting the Knox coordinate for that point, we are also able to propagate the grasping point to the canonical space. And actually, in the second example, you can see that the grasping prediction is mirrored. It's actually wrong. So it's actually predicted on the wrong side. But in the later step, you can see that how the algorithm is able to self-correct this kind of error. Okay, so now we mapped all the observed points into the canonical space. And then in the next step, we need to complete the shape in the canonical space in order to provide the labels for the unobserved surface. So the shape completion for rigid objects is actually a well-studied problem with many prior works. And here we actually use a network structure that's very similar to a GarmentNet. Basically, what we do is that first scatter the point net features into a 3D volume, and then use a 3D CNN to convert the sparse feature into a dense feature volume, and then finally use the implicit function to produce a detailed high resolution surface. So there are many successful stories of using like such network for rigid object shape completion. However, for garments, because of their thin structure, it's actually a little bit tricky to select the right 3D shape representation for them. So first, it is quite obvious that occupancy grid is not very suitable to representing thin surface, right? Since its accuracy is actually limited by the voxel resolution. However, if we just directly increase the resolution, we will result in a very sparse data distribution, and also requires a lot of like high memory consumptions. On the other hand, using like representation like sine distance function, we are able to represent very accurate thin surface by giving different signs for the voxels of inside and outside the garment. where the zero crossing surface precisely describes the location on the surface. However, TSDF representation can only describe the watertight surface with no holes. And therefore, if we directly extract the zero crossing surface, we'll get additional surface around the garment openings like their nest and waist. So to address this issue, we introduced a new shape representation called generalized winding number field that allows to representing thin surface with openings. So first, what is winding number? So we didn't invent this. This is actually like something already used in many different fields like physics. So winding number is basically like defined by, so for a given point, it's defined by the signed length of the projection of a curve onto a unit circle. So the value is eventually normalized by 2 pi so that the actual value is ranged from 0 to 1. So intuitively, for a point that is inside a surface, the winding number field is equal to 0, and for points outside the curve, the winding number equal to 0. And if we compute the winding number for all the locations in the space, we can get a winding number field. And we can also extend this definition to 3D by replacing the 2D angle to solid angle in 3D. So the next question is why we use this winding number field. What are the special properties make them desirable for our application, right? So actually, if the surface is watertight, then the values will be constant 1 inside the surface and also constant 0 outside the surface. It is basically the same as like occupancy grid, and it is not that exciting. But however, when the surface has opening, things become more interesting. So for those surface, we can observe a very smooth transition from the inside positive value to the outside negative value on the opening area. So in fact, the function is harmonic or smooth everywhere except the discontinuity on the surface. Therefore, by detecting the gradients on this winding number field, we can find both the surface and opening. And by using the gradient magnitude, we are able to distinguish the surface and openings. So here is an example of winding number field and its corresponding gradient magnitude. So we can see that on the gradient magnitude on the openings is significantly smaller than the gradient magnitude on the surface. And then we can use that, like by setting a threshold, we are able to distinguish these two types of like opening and surface. Okay, so here are some example results for the shape completion step. So on the left is the input canonical coordinate prediction and the ground truth surface. And on the right, you can see the prediction results by using different shape representations, which is TSDF and also occupancy grid. And here is another example. So in the last step, we would like to map the completed 3D mesh back to the observation space, which is the original input point cloud. So eventually, this output representation will be able to describe the full configuration of the garment in the original observation space, including the occluded part. Okay, so actually for the last step, there are two possible approaches for these steps. So one approach is to just directly use physics simulation to estimate the pose of the completed mesh with the predicted grasping point. And the other one is to learn this mapping using a neural network. So we actually implement both approach, and also we're gonna kind of discuss what's their advantage and disadvantages. So for the first approach, we will use the predicted grasping point from the first step and the completed 3D mesh in the second step, and then simulate how the class will fall under gravity, and then use these simulation results to basically use that as our final estimation of the class pose in the observation space. So the advantage for this approach is that it can always predict the results that actually looks physically possible. However, the disadvantage is that it is very sensitive to any errors happened in the early step, such as incorrect grasping prediction or like invalid mesh reconstruction. So that's this approach. And the second approach is to directly predict the warp field as a natural implicit function that basically is taking a sampled position P and is corresponding feature as input and output the warp vectors for that position. So here's the warp field is basically the XYZ locations of the point in the original observation space. So the features that we used for this network is actually the original point position in the observation space or the task space for all the observed points. We don't have those numbers for the unobserved points. And then also concatenate with the original PointNet++ feature. So although this kind of, by training a network to do the warp field prediction may not always guarantee the physical, the result is physically possible, but the network actually gain additional robustness against the prediction error happened in the early stage. So if we measured quantitatively in our experiments, the second approach is always can produce something that has less error. But visually, actually, the first method typically gives better looking results. Okay, so here are the example results. So basically, on the right, you can see the ground truth mesh and the predicted completed 3D mesh and also the corresponding grasping point. And on the right is basically how we can map the completed 3D mesh to the original observation space. And we compared with ground truth and two different approach for doing this step. So in this example, you can see that the network actually make a mistake on predicting the grasping point. So it should be on the right hand, but it actually predicted on the left hand. And if we use a physical simulation, the predicted pose is also wrong because of the prediction error. But the warp field prediction actually able to correct this error because the feature actually contains the original point locations in the observation space. Okay, so here is another example for pens. And again, this is another example of showing how the warp field is able to correct this kind of mirrored prediction error. And okay, so now we can put everything together to form this end-to-end framework GarmentNet, which consists of three major steps. So first, canonicalization maps the input point cloud into the canonical space. And the second, complete the 3D mesh in the canonical space. And then finally, warps the complete shape back to the input space. And the final output representation describes the garment's full configuration using complete 3D mesh with per vertex coordinate label. And here I'm just going to show you some of the results of the algorithm. On the top row is a prediction, and on the bottom row is a ground truth. So here is actually a typical failure case that you can see that the straps of the top is actually missing. The algorithm do have troubles to predicting those kind of structures. Okay, so to summarize, the key idea for GarmentNet is really the problem formulation, where we formulate the post-estimation problem for garments as a shape completion task in canonical space. So by leveraging the category level priors, the algorithm is able to infer the full configurations of an unseen garment, including both observed and unobserved surface. And in addition, we also propose to using van der Nijmegen field as a new shape representation in deep learning, which is suitable for representing cloths or garments that consist of very thin surface with openings. So for this project, we actually mostly talk about perception. And the only step that involves the robot is the step 0, where we ask the robot to pick up the cloth in order to observe it. However, this very simple action is actually very critical since it significantly reduces the difficulty of the perception task by increasing the visibility of the cloth. So this got us thinking that what if the robot is able to use their own actions to physically unfold the t-shirt? Well, it's just make the perception algorithm so much easier. All right, so in the next project, we'll push more on the interaction side and then try to see whether we can use the robot's physical action to actually unfold and reveal the unseen part of the cloth. And this work is done by Hui Ha, who is an undergrad student in Columbia University. Okay, so first, let's talk about the task of cloth unfolding, whereas the objective is to simply maximize the visible surface area of a cloth. Right, so the task is actually very, very useful since it's often the common first step for almost any cloth manipulation pipeline. So by unfolding a cloth, we are able to reveal many key features of the cloth that is initially hidden and therefore simplifying the later planning steps. However, while the objective of class unfolding is very simple, training a policy that can do it effectively and efficiently is quite challenging. So here is a video of 2 robot arms that is trained to unfold a t-shirt using pick and place. So you can see that it actually takes a system a very long time, many interaction steps to make some progress, not much progress. And actually, if the corner of the class is unfortunately not visible in the initial state, the system will not be able to make much progress. And similarly, if the class is larger than the robot's reach range, then the class will actually never be fully unfolded by using just pick and place. And this system actually reflects a common limitation for many prior works in class unfolding, whereas the robot actually use only quasi-static interactions like pick and place. So over the years, there have been so many algorithms, like sophisticated algorithms and methods proposed to model deformable objects. However, the final system are actually often still highly inefficient. So they can easily take hundreds of steps just to unfold a very small piece of cloth. And actually here is an example of the robot actually takes more than 100 steps to unfold this small class. So as a result, many of the works in class manipulation considers a much simpler cases, where the class is almost unfolded as the initial step, and where the key features of the class is already visible in the initial state. But let's take a step back and think about how would you unfold a large class like a blanket? Will you actually carefully pick and place every single corner of the class? Probably not, right? So you'll probably do something similar to this. So where you'll probably grasp the blanket with 2 of your hands, stretch it, and then fling it over the bed with high velocity in order to unfold it. All right, so from this example, actually we see that what's the robot really missing is the capability of using high velocity dynamic manipulation, which is something that we actually are constantly using in our everyday life in order to improve our physical reachability and also action efficiency. So concretely, there are 3 advantages of using high velocity dynamic actions in comparison to quasi-static actions. So first is that they are much more efficient, right? In the earlier example, we can see that a single fling action actually can be more effective than many more quasi-static pick and place. And second is that dynamic manipulation also helps in expanding the system's effective reach range. So like what we said earlier, since most of the class are under-actuated, the robot actually does not have direct control over the positions that is far away from the gripper. However, with high velocity action, the system actually gains an opportunity to actually manipulate the part of the object that is out of contact, or sometimes even out of the robot's reach range. And finally, dynamic action also is generalizable, since that they no longer rely on precisely identifying specific key points on the cloth. And later we'll show that a policy that is trained on squared cloth or rectangle cloth can also generalize to complex cloths like t-shirts. Okay, so using these ideas, we designed our system called FlingBot, which is a fully self-supervised system that is able to achieve over 80% of coverage with 3 interaction steps. So in our experiment, we used 2 UR5 arms and also 2 RGBD cameras for the setup. So the first RGBD camera actually take a front view of the workspace after the class being picked up. And the second camera actually take top-down images for predicting grass positions. And what the algorithm actually do is to take the images as input and then output the parameters for the Fling primitive, which we'll talk about in a bit. So after each of the action execution, the top-down camera will actually capture an image of the class before and after the action is executed, and then compute the delta coverage of the class and use that as a supervision signal to supervise the network training. And then in the end of each episode, the system also automatically resets the class initial state by just randomly pick up the class and drop it back to the workspace. So as a result, the system is able to learn by itself with very little human intervention. Yeah, from time to time, we still need to swap out the class, but yeah, within one session, they can do it by themselves. Okay, so now we are gonna talk about this Fling primitive, this two-arm Fling primitive, which consists of a few steps. So first, the arm needs to find two grasp points to pick the class up, and then stretch the class, and then use a high velocity swing to fling the class forward, and then finally place them back down back to the workspace. So for each steps in this sequence, there are actually different parameters that controls each of the steps. So in another word, in order to perform those primitives, we need to choose such as where to pick, how far to stretch, how fast to fling, and finally where to place. And for the task of class unfolding, actually some of those questions has pretty straightforward answers. Right? So for example, for the second step, we pretty much want to stretch as far as possible as long as you don't tear the class apart. And then for the last step, we just need the system to place the class down back to the workspace that is still reachable by the robot. So that is also pretty straightforward. So as a result, what we really need the system to learn is the first step, where to pick up the class, and also how to fling, like what's the fling speed. However, for now, let's first fix the fling speed and then focus on the first step. So what we just did is to take a complex multi-step action primitive and reduce it to a much easier problem, which is basically finding two good grasping points. However, we'll see that actually learning these two grasping points is still requires some careful thought. So it is because there are a few constraints that we actually need to impose on the grasping point selection. So the first one is what we call crossover constraint, which basically means that for the two robot arms, the right arms should always stay on the right, and the left arms should always stay at left, without crossing to each other workspace, so that they may cause potential collisions. And the second constraint is grasp width constraint, which basically means that we don't want the two robots to get too close or too far apart. So given these two constraints, we want to design our action parameterization in a way that they can easily satisfy these constraints. So again, what we need to output is two variables, left and right. So here I basically denote it as L and R. So one option is to just directly predicting the parameters for L and R. However, the constraints can get entangled together. So you can imagine a network to predict the 2 points independently, and then have a set of heuristic method to reject the invalid pairs. But it can be a little bit messy, and it's a little bit hard to actually do it correctly. So another option is actually to change the parameterization. So instead, what we're going to predict is the center points of L and R, and then we'll also additionally predict the rotation angle that describing the rotation of these two points, and as well as the width between these two grasping points, which is described by W. So this parameterization actually allows us to directly compute the L and R using very simple trigonometry. And as a result, all the computed L and Rs will naturally satisfy all the constraints. So now what we need to do is to have a method that learns the parameters of C, theta, and W. Okay, so one approach, again, is to directly predict all those parameters as scalar values. However, we want an algorithm or method that is slightly more sample efficient. So what this means that what we want to do is to use the structure of the problem to inject some inductive bias into the learning process. So for the class unfolding, the best grasp position actually has a few important equivariance that's with respect to the input image that we want to maintain. So first is obviously translation, which means that if the class is shifted in the workspace, the corresponding grasp point should shift together with respect to the input. And similarly, we also want to maintain the equivalence of rotation, which means that if the class is rotated, we also want the best grasping point to rotate with the same angle. And also for scale, although the size of the class may actually affect the class mass and therefore influence the fling speed, however, it shouldn't really influence the selection of grasp position. So to do this, we use a spatial action map as a value network in order to evaluate all the grasping candidates. So the key idea of spatial action map is that whenever we try to reason about the rotation and scales in the output, we can offload this kind of reasoning by actually instead transforming our input image. So in another word, rather than rotating and scaling the grasp parameter, what we can do is rotating and scaling the image inputs and then infer the grasp scores for a fixed grasping parameter. So here is how we apply the spatial action map in this problem. So given an input image, like a top-down image on the left, we can actually scale and rotate this image to obtain a collection of transformed input image. So here, the different scale actually will corresponding to different grasp width. And then different rotation will corresponding to different grasp angle, which give us the theta. And then the output is basically a dense value map where each of the pixel corresponding to one possible center locations for the two arm grasps, which is basically the C parameter. And the action selection is done by simply pick the pixel with the highest grasping value among all the scales and the rotations. And the value network is trained to predict the delta surface area with self-supervised learning, as we described earlier. So here is a simulation environment that we used to do our application study. We actually has a variance of a self-gym to adapt to our evaluation and also like kind of set up our experiment. So our policy is only trained on rectangular cloth of different sizes. And we also explicitly test the algorithm with large rectangle class that is actually larger than the system maximum reach range. And this is intended to test our policy's expanded effective reach range. And lastly, we also test our policy on shirts that is actually not trained, not C during the training for the policy. So as we can see that the policy, although it's only trained on rectangle cloth, is also able to do decently well on t-shirts or like different type of shirts. So now we can actually see the system in action in real world, which is the most fun part. So here we actually compare our system.
Shuran, I think I missed some parts. So how is again where is the supervision coming from for the points to pick up?
Yeah, so the supervision is only like the delta coverage, which is computed from the top-down camera. So the camera can see before and after the action. And then they compute a value to kind of provide like whether this two grasp points is good or bad, whether you increase the delta coverage or decrease. And it's actually trained with regression.
I see. And this is trained in simulation.
It's trained both in simulation and real world.
Okay, got it. And what do you? Sorry, that's not what do you use for simulation here? Are you still using Blender as the simulator, or
yeah? So it's actually a combination of both. I think we use the SoftGym, which is I think NVIDIA Flex as a backbone to simulate the class physics, and we use Blender to render the image.
Mm-hmm.
Yeah.
Quick question. So just so that I understand, so you do try all possible, basically, the value network that rotates and figures out which are the best places to pick up. You basically try all of them basically, and then see how much coverage increased, and that's really the supervision, and you kind of repeat it.
Yeah, so each time the system actually only pick one. So the supervision only has one pixel or like one pair, but the input is all the variance, and then so during testing, you actually need to like input all the variance of the input and output all the values, and you pick the maximum one. But the supervision only can go through for the one that you actually pick.
I see. Yes. So this needs to have like a good initialization or something, because in the beginning it's kind of garbage, right? So you could pick random points.
Yeah, so actually to train this network successfully, we don't need like a very special way of initializing it. And I think this is actually because grasping a cloud is relatively easy. So you can always actually grasp a cloud. Actually, as long as it's on a grasping point on the cloud. So you can actually get supervision from the very first try. Yeah.
But I think one, maybe it's a question for later, but just quick thing. So when you were showing this person unfolding the bed sheet, I think that the most tricky part in bed sheet is that not that part. I think for me, it is picking the right points in the beginning, because if sometimes you pick the wrong points, you put force and then it's entangled completely, and then you have to find the other two corners. So it seems like a pretty hard supervision to decide which 2 points to pick if it is completely mushed in the beginning.
Compo together, right? Yeah, I think that the key is that if you want to do it only with one round, one try, it's tricky. But if you give yourself like 3 times, like if the first time you didn't get it right, the next time, I think this kind of has like fling action always kind of like increase some of the surface area. And then that interaction can give you a little bit additional information. And the next step, you can choose a better grasping point.
Okay.
Yeah.
Actually,
but then the cloth has been flown away far away.
That's because you're trying too hard.
Okay.
I was actually curious about the comment that the fling action will always increase the coverage. I was curious. I was like, well, are there actual examples that will make it worse?
Yeah, I think it's correct. It's not always increasing. It actually sometimes decreases as well.
Are there like specific configurations where you pick it up where it like makes it worse, or is it because I was trying to figure out what they were, but I couldn't figure it out. I was curious if you know what they were.
Yeah, actually they are like so if you take a look on the grasping point that the system selects, is whenever there is edge visible, they always try to go for the corners and edges. And it's actually if you just pick up the class in the middle, and the worst case is actually pick up 2 layers of class, and then it's actually folding the class together. So that actually reduces the coverage. Yeah. Any other questions? Okay, so I will probably just show more of the results. Okay, so that just played is basically a comparison for Flingbot and pick and place. And here's another one that we can watch. So basically, in the bottom, that's we plot the coverage with respect to interaction steps, and that's basically a measurement of efficiency. So you can see that for Flingbot, it can is able to kind of fully unfold the class with 4 steps, and the pick and place take a lot longer, a lot more interactions to make much less progress. And this is another example of a shirt that the algorithm actually didn't never really trained on shirts. They actually only trained on rectangle cloud.
This is super cool. I love the results. I noticed that like there's like in the beginning there's like one thing that actually grasped and like kind of
that's the random initialization. So they they randomly set up the state so that the class is back to the crumple state. Yeah. Yeah. So here is just more results. Yeah, so here's more results, and if your internet has some issue not able to see them in action, there is a link to the website that actually has more results like this.
So how many training samples do you use to get to this result?
Yeah, so actually it requires a lot of training in simulation. So I think it's at the range of several 100K training iterations in simulation, but in real world, we don't need to have a lot of training data.
So and each sample here means that full primitive is one sample.
Yeah, so one grass, one fling. I think that's one sample. Yeah.
Got it.
Okay, so here are some qualitative results and comparisons. So we basically compared against the 2 quasi-static baselines that use pick and place and pick and drag. And here, like in most of cases, Flingbot is able to reach over 80% of coverage within 3 steps, while baselines most of the time, or like the quasi-static baselines, more likely to stack around like 60% without making much more progress. So here we also actually include a variant of our approach that actually learns the Fling speed on top of the grasping strategy. And we actually use reinforcement learning to learn that Fling speed. However, we can see that it's not significantly better than Flingbot without predicting the Fling speed. So we actually prefer the simpler version as our final approach. Okay, so this is Flingbot. And I think in summary, what we did here is trying to demonstrate the effectiveness of dynamic manipulation for class unfolding task. And more specifically, we can use a dynamic manipulation to improve the system's efficiency, basically reach a higher coverage with fewer interaction steps, and also increase its effective reach range, allowing the robot to control the positions of out of contact points, and also achieve a good generalization to out of distribution cloud. So that is like pretty much about the two projects that I want to talk about. But so here I want to talk about like have a way to summarize the two of this project. So earlier today, I started my talks by listing out a set of unique properties of deformable class that actually make them hard to deal with. However, I want to also end my talk by telling the other side of the story. So what are the class like other properties that actually making deformable objects easier to handle? And while we are talking about them, I will also recap on how we actually leverage this kind of properties in our approach and discuss how they could potentially inspire or influence future research directions. Okay, so first is a strong shape pairs. So because of the functionality of garments is mostly designed to cover all body, so they often actually share a very similar topological structure. So for example, although different shirts may look very different under different configuration, but different shirt actually looks very similar. At least they have very similar structure under the same configuration, which provide a very strong category level pair that can be used for the machine learning algorithm. So another way to think about it is that for rigid objects like chairs, we can easily find different versions of them has like 2, 3, or 4 different legs. However, it is actually really hard for us to find a shirt with 1 or 3 different sleeves, right? So in our project, so we kind of leverage this property by defining and using a category level canonical space. And the next question is whether we can enable the machine learning algorithm to automatically discover a much more complex representation for category level garments by exploiting this kind of shape pairs. So for example, we maybe only need to represent or learn a few critical points on the garments instead of the full 3D geometry. However, we kind of want the system to automatically learn which are the critical points instead of we manually define those points. And the second point is that is the fact that deformable objects actually much easier to grasp. So here, I definitely don't mean that they're easy to manipulate. I'm just talking about grasping. So for example, for rigid objects, there's actually, given any rigid objects, there's actually a very limited number of good grasp poses. And they're often very sensitive in terms of grasp orientations or gripper sizes, which means that if the pose estimation algorithm is slightly off, the grasp will fail. However, for deformable objects, it's different. Like we can basically grasp it from any locations and any orientations as long as it's part of the object. So we actually use this property in both of our projects. So for example, in the first project, we just asked the system to randomly pick up the class in order to get observation. So that can always be successful. And then in the second project, we're simplifying the two-arm grasping problem by actually ignoring the grasping orientation for each of individual gripper. So if you notice that for the L and the R, we only predict the location. We actually didn't predict the orientation for each of them. And however, precisely manipulating a deformable object to a target configuration is still a very challenging task, and it requires much closer integration between perception and planning. Right? So for example, the system may need to estimate the garment's pose in order for them to do action planning, and also learns to use its action to reduce ambiguities for perception. So I think all those are like interesting research, like future research directions to study. And the last is that since deformable objects, they are soft and compliant, they are often in general much safer to interact. So because we just typically has less concern about collisions. So as a result, it's much easier to set up a self-supervised learning framework for them. Since the objects are soft, so it is in general safer for the robot to actually play with them by themselves. Just like typically we give baby soft toys before we give them rigid ones. And similarly, it's also safer to apply high-speed actions on deformable objects. And all these properties actually is what makes training Flingbot in real world possible. And so the next question is here is actually, can we take this idea of self-supervised dynamic manipulation one step further and allow the robot to acquire those dynamic manipulation strategies automatically? So far what we have done is first kind of identify which manipulation primitives such as Fling that is useful. And then we ask the network to predict the parameters for those primitives, right? But like there are a large family of dynamic manipulation strategies that out there, and it's actually impossible for us to engineer every single one of them. So can we allow the robot to discover all those useful strategies and automatically select which strategy to use in order to achieve its goal? And I kind of believe it is possible and also absolutely necessary for achieving efficient manipulation for deformable objects. And I think that's the end of my talk. And I want to finally thank all my collaborators that make all these projects possible. And also thank you for listening. And I'm happy for questions or discussions.
Great talk. Thank you so much, Shuran. That was super cool stuff. Let's see. I want to get going with some of the questions that we've been having on YouTube. Okay, so I will start with the GarmentNet. Oh, sorry, I will start with the Flingbot because we just talked about this. Quick question: could the Flingbot disentangle a knotted T-shirt without tearing it apart? Hopefully.
Oh, it's never trained to do that task. So for all the training data, we never knotted to let them untangle. Let me think whether it is possible.
I guess if it's not super tight, you could.
If it's super tight, then it has it probably needs some force feedbacks in order for them to kind of know how hard I should pull them apart without tearing them. But if it's loosely tight, I feel if the training data provides that, so basically what the system needs to learn is finding a two good points that's kind of stretch them. And if they're lucky, I think it's possible to untie a knot, but I think it's definitely a much more challenging task. Yeah.
Another question from Yasutaka Yasu is that it sounds like most training is done in simulation and didn't suffer too much from the simulation to the real gap, unlike other tasks. Is this gap a challenge or easy for cloth?
Oh, I think there is still a big gap. So for example, for the first one, I think for the second one, actually, we don't observe a lot of gaps. I feel the system actually trained in simulation, deployed in real, is already kind of works reasonably well. I think that's probably because of the perception requirement is much lower. It just need to kind of detect edges and corners. But for the first one, for the first project, actually, it's quite there is pretty obvious gaps between simulation and real. And it's actually also very challenging to train that network in real. As you guys pointed out, getting this Knox label, a dense Knox label in real world is very hard. So I think in order to bridge that gap, we either need to kind of rethink about problem formulation or think about smarter ways to get label data to address that gap. Yeah.
Okay, great. So let's moving on to the GarmentNets paper. Is there a link to the GarmentNets paper?
It's soon, coming soon.
Okay, great. And then I think there was a question is that if you pick up the same cloth multiple times, how consistent are the results? And could you merge results from multiple picking to improve it?
Yeah, so if the pick point is the same point, actually because of the gravity force, and it actually almost always get into a similar configuration. So, but if you pick up a different picking point, you actually get different pulses. Yeah, and actually picking up several times and then try to average the prediction. I think that's actually a way that we are thinking about how to get ground truth label, right? So in real world, if we start with a fully unfold class and we just pick it up, maybe that's a way that we can get some kind of real world labels.
Okay, great. One more question, which is to infer the unseen parts of a cloth for like an unknown clothing item that you've never seen. Like, will you infer a distribution over its category, like what the category is, or like what are your thoughts about this direction?
Yeah, so in order to do that, it's really kind of like depends on the priors, how strong the system has the prior. And I think for garments, luckily, although the textures can be like very different, the details can be very different, but their geometry actually are very similar to each other because of the functionality. So for garments, or at least typical garments and not designer brands, it's probably like reasonable, like okay, to kind of infer the unseen part. But if it's a class that is out of distribution, it's definitely going to cause some problem. Yeah.
Great. Okay, great. Thank you. Thank you all the audience for questions. I would like to pass it on to the panelists. If you have any, we can start from short or jump directly into big questions. Totally up to you.
Yeah, I have some questions. So should I start from the short ones or?
All of them.
Okay. Yeah, I think one quick comment is I think your figures are really cool. I was searching on the site, what do you use for those figures? And it seems like one of your students had this Pi Bullet and Blender renderer. Yes. But they are really cool. I send a link to all of my students. So
yeah, that's Hui. Actually, he developed this really nice tool that basically whatever you do in Self-Gym or Pi Bullet, you can directly port it into Blender, and you have nice renderings.
Yeah, it is really cool. So one maybe it's mid-level to high-level question. I found so like the two projects you presented, they are somewhat on some opposite ends of a spectrum, and that spectrum is how much 3D is needed for the behavior. So then in the first project, you really trying to get this geometric modeling going to understand which points to pick up and get pose and etc. But in the second project, you said, oh, let's ignore all of that. Let's find 2 points and then let's fling it.
Exactly. Yeah.
So do you think these two ends will merge somewhere, or?
Yeah, I think that's a very good question, and I think they should definitely. And I think the way I imagining is that the other direction. Actually, I feel Flingball is probably a good first step. So if you want to deal with a class, the first step is to use some kind of action to get into a state that is easy for perception. So I think when we work on the first project, the thing that we feel reliably we can use is pickup. We haven't like go through the Flingball. We haven't had Flingball yet. So, but imagine if you have like a robust strategy that you can manipulate the class, then you can actually get it into a state that you don't need to have very sophisticated perception. But whether 3D is important, I think, yes, it is. And especially when you are trying to deal with like goal conditions manipulation. You want to fold your class or get the class into a state that it need more precision in terms of manipulation. I think getting the accurate pose or knowing the correspondence of this garment or to other garment, I think all those things are very important.
But I don't know. I feel like I think that towards the end of your fling, what you were saying that deformable manipulation, like just few points might be good enough. And I feel like maybe that's what we do as humans. I don't recall. I think whenever I have to unfold my t-shirt, I just pick up the shoulder. No matter whichever form it is in, I just fling it. And I really like this idea.
Yeah. I think yes. Maybe we don't need the full configuration like what GarmentNet is inferring. But the question is how we can find like a good critical points, and it may change from task to task. It may change from garment to garment. So ideally, it's something that the system learned through either interaction or like the interaction perception loop, so that they can have a compact representation.
Okay.
Actually, speaking of the compact representation, I think this is such a like fascinating area because they're, and by the way, I really like the figures as well, and I love the story as well because this is a very hard talk to ask questions of because you'd say, oh, I know a high level question I'm going to ask, and then oh nope, answered. But I'm just curious about what I was thinking about with these compact representations of like the shape and sort of, for example, getting rid of a full 3D is. Do you have any thoughts on like once you start being able to fold these objects and you go from, okay, you do the fling bot, which is a lot of fun. And then you want to fold it into compact sort of, you want to fold it into a specific folding thing. In some senses, there are there's sort of whatchamacallit, there are equivalence classes of foldings. And I'm curious if you have any thoughts about how you might represent, okay, fine, if you work for Old Navy, I'm sure there's a very specific way that you're supposed to fold the t-shirt. But are there equivalence classes for example, how many ways can you fold a blanket? And presumably you don't want to keep track of all the combinatorial space. And do you have thoughts about this and like how you might represent these things in a way which is like not quite 3D, but has some 3D in it?
I might understand correctly, it's like how we can define like tasks like folding that can have many different ways, but in a way that's like defining the task in a more compact like.
Yeah, like what's a represent, like if I take a large blanket and I'm going to go to my post-COVID picnic and I put everything, I fold it over, I need to get into my backpack. There are probably tons and tons of different ways. There's 2 to the n sorts of ways. You make a decision about how you fold it. Any thoughts about how you might represent these sorts of somewhat more or less the same states in the sort of 3D parameter space?
Yeah, exactly. So I think that's actually related to like how it's related to the same question, like how you want to give the reward function or how you want to define your objectives, right? So I think for example, if your goal of folding is so that you can make them into a compact state that is as small as possible so that you can stack them into your luggage, then maybe your reward is just the surface area. And then the system figure out, maybe they want to fold it, maybe they want to roll it, maybe they want to do whatever with it so that the volume is small. So if that's your objective, then maybe we don't need to define the configurations of the goal state. We just need to define the objective. And I think for sure, it's actually the reason we fold them. Like part of it is so that it can reduce the surface area. I think another one is like in a way that we fold it so that it has less wrinkles, right? So maybe that's another objective that we can add into the reward function, so that if everything will turn out well, they can learn a policy and then maybe fold it better than what we can define.
Oh, okay. So following up on this, the thing I really like about your research is like a lot of that is super self-supervised, and like the supervision really is coming from what happened instead of like an RL system. But in this one is in simulation. But I think in the past it was also in real life in pick and place. Was it?
Yeah. For pick and place, mostly in real, and I think in for this one it can also train in real world. It has a top-down camera, and it can collect the reward. But it do need, so for the Fling, it do need a lot more training data. So if we directly train on real, it's gonna take the student a long time.
I see.
Yeah.
Okay, great. Deepak, maybe have a.
Yeah. So I have a maybe again a high level question. So I find it like across all your works a very nice pattern of creativity that you take complex tasks, you find right primitives, and you push the difficulty from the action side to the vision side, and action side becomes simple, like with 1 step or 2 step, and then you show that okay, having a good perception system can actually help make these tasks look easy, although I'm sure projects take long time to get to that beautiful results. So what do you think is what do you think the path looks like for less creative people like me, where we are always stuck in thinking about what is the most general way to solve this, and then you come up with this is have a fling board, have a tossing board, have a picking board, right? So what do you think are the positives and drawbacks of this, both pros and cons of this way of doing things? And what do you think, like, could we have like a library of skills which will eventually help us solve all of those tasks together?
Yeah, exactly. Yeah, I think that's a really good question. That's something that I ask myself every day too. Okay, so I think this is like, it's actually like either a feature or a bug, right? So because I come with like a computer vision background, so I actually knows better about how to solve computer vision problem than how to solve control problem. So this is a natural tendency, like how we can simplify the control problem, and then let's focus on the perception. So that's like why like you can see this kind of pattern in my work. But I also do feel the limitation. So I think the last slides I kind of show that there are so many like interesting and useful primitives or skills that the system can learn, but we highly constrain them. So like this kind of complicated Fling action, we just predict 4 or 3 different parameters. And for tossing, we actually just predict 1 parameters, right? So we actually highly constrain the skills or the capabilities of the robots. Although it makes it sample efficient, it makes it practical in real world. But I think to move forward, we really need to think about how we can like either find a middle ground or find a way that can relax that assumption. And I think like learning like effective primitives, like learning like either dynamic primitives or quasi-static primitives, and then have a like what you said, have a library of skills, and the system knows which one to use. I think that is probably what we should think about in the future. Yeah.
Cool.
Actually, going off on that, sort of like learning this library of skills, one of the things I really like about the Flingbot as well is it's this it's just not careful. It's like not careful movement. It's the way that, I just remember when I took a manipulation class, the first thing we were shown by Matt Mason is he showed us this video of Julia Child chopping stuff and doing everything in the kitchen. And then he basically said, okay, all the stuff we're going to see in this manipulation class is, you actually have grasped it, and everything she's doing. She's an excellent chef. None of it is this careful, controlled grasping. And I'm curious about the dynamic stuff. Like sometimes it feels if people are limited by the fact that things cost money. You can't, for example, just take you take one of these arms and just sort of plop it in a house and let it cause havoc. And I'm just sort of very curious, like if sort of cost was no issue, and you could have robots that would run around in the real world trying these dynamic interactions that are not careful. Mm-hmm. I'm curious if you had tasks that you'd love to tackle with this, or like manipulations you like to do, if you could basically just let the robot loose in a million apartments, and what would you do?
Yeah. Can you guys still hear me?
Yeah, we can hear you.
Okay, let me see. Okay,
right,
so
yeah. Good.
Yeah, I think that's a really good question, and I think there are a lot of people actually thinking along that direction. Right? Like Avinath Gupta has so many works that's like robot in your homes, and the whole idea is that if the robot cost is lower, then we can actually let them go like everywhere, and then we don't need to worry too much. And I think one thing I want to add to that, to kind of like another way to think about how we can enable that, and also related to today's talk, is think about deformable objects and also deformable robots. Because they're soft, because they're compliant, they're probably safer to interact with the world. Probably will have less concern about they're causing like issues or they're hurting themselves. So maybe that's another way that's apart from lowering the cost, is another like a way that we can enable this kind of in the wild robots.
But you could also even imagine with the deformable robot, like if I have a glass over here, well, there you go, now I can see it. You can knock stuff over and cause lots of trouble. You can if you can in order to apply a reasonable amount of force, like open my my poorly assembled drawers in graduate school, I have to really pull on them because I assembled them myself from IKEA. A lot of these things, if you have a software, but certainly can manipulate stuff. But I guess there's certain things where I feel as if in order to learn how to do it, you need to
make mistakes.
You need to make mistakes. You need to break things. You have to tip over the dresser, or I guess are there sorts of things that you think are kind of off limits?
Yeah, exactly. I think maybe we should just like treating our robot more like our kids. Like give them a little bit more patience and don't worry too much. Let them make some mistakes and in the real world so that they can actually grow. But it's very hard, maybe. But I think that's indeed a very exciting direction. Yeah.
Okay, I have one more. Sorry. So there is this for this deformable objects, right? One of the main signal that we use as humans, even more than vision, is probably touch, right? Which probably makes things much more easier. And yeah, but I think here the touch was missing altogether.
Yeah. So we don't have the skill or the expertise to actually do the, well, actually we don't even have the hardware, like as you see in our lab right now, like to actually use tactile. But I agree with you. I think tactile is very important. And I think for deformable objects, it can actually tell a lot of information, like the material, for example, and the other physical properties about the clock. And maybe that can be used to predict the Fling primitive better than we just take a visual input and predict the Fling speed, which is turned out to be not very useful.
Great. Okay, I have a question about this. Yeah, the deformable object is like a super hard problem, and I really like it. You kind of solved it really well. But I think there's this question of like the categorical prior. Like in a sense, the first work really focused a lot on the categorical prior, and the second one is too. But also, like you only train on the rectangles, right? And so it kind of generalizes really well when in this domain of like manipulation. If you just wanted to spread it up. What do you think about, I really think the problem is when you go to a more general deformable objects like ropes, or there's a question about how would you disentangle a headphone? Yeah, what are your thoughts in, categorical prior with the deformable models?
Yeah, I think that's a general question, like in terms of machine learning, how much we want to rely on parse, how much we want them to be like just general. I think well, maybe the answer is like if it's in a category or in a task that we have parse to leverage, then like go for it. But I think when we don't have a lot of prior, like for example, in the world, like headphones or things that we cannot categorize it with like particular object categories, then maybe interaction is very important. So interaction can help you to kind of know more about this object. So you can untangle this wire so that you can reconstruct it. You can unfold a shirt so that you actually see the weird cut on the shirt. So when we would deal with out of distribution, then we need to have more observations. And how to get those more observations is through like interaction.
Right. Yeah, I mean, this is also interesting. It also comes back to this idea of like improving your perception model by the self-supervised kind of like looking at what happened. But then right now it's simulated. I mean, this kind of goes back to teaching your robot like a baby, because once it does something, it's all in a different state, and you gotta bring it back there, which you could actually, that's what you maybe do for babies. But yeah, like, is it actually, maybe listening to your talk, I'm like, maybe we figured this out. Maybe the way to have the feedback to perception is really just try a lot and then use that as a self-supervision.
I think certain tasks is easier to define the self-supervision. There are tasks that's harder, right? Like I think like fling, tossing, or picking, it's relatively, we can get very dense supervision now in real world. But if it's a long horizon task, I think that's why like a lot of like RL, like that's the major difficulties that most of the RL work is trying to address. Is like if you have a very long horizon task that has a lot of different steps, in the end you get a positive reward, then it's probably really hard to directly like self-supervise it. I think a lot of like Deepak work that's actually trying to address those problems. Yeah.
Great.
So yeah, so let me make it slightly more controversial. I have these headphones in front of me. I was really thinking, how do I disentangle it? And it seems so hard. I mean, I don't know. Am I generalizing? I don't even can pinpoint. If you were to make it a library of primitives, I might require infinite. I don't know. Is it?
So you're thinking about untangling them, or like what has
disentangling them? Like, I mean, entangling is easy. Just keep them in your pocket and take them out after 2 hours. They are entangled. I think disentangling is really hard. And I like this. Maybe instead of the primitives of the control, what we are really looking for are primitives of the visual part. Like this, we always go about finding one key point, which like in shirt it's shoulder, in earphones it's a centerpiece which can be, after which you can see it hanging. Maybe that's the part that is generalizing across scenarios, like your key point things, and then the control part just falls out, just trying to enable that, and is not really a primitive. I don't know.
I think that's actually get to the point of affordance, right? So like the visual affordance is like looking at this object, what I can do with it, like whether I can pick it, whether I can like grasp it, or I think that's like the general idea of like visual affordance. And but I still feel like the affordance and the primitive or like the action, they're actually very entangled. I don't think that's one is more important than the other. So without like actually thinking about what action that's you actually gonna apply, I think just by labeling the pixels is not that it's not that useful, I think. Yeah.
So what do you think, is a very open-ended question, what do you think could be a way to learn generalized affordances? Like same affordance between earphone and my t-shirt.
Yeah, so okay, so this is a very hard question. I will just try my best. I feel, okay, one example is through predictive model. I feel predictive model is actually a very general way of formulating it. So if you like predictive model of like state, action, and predict the future state. So that's a natural way of self-supervision, right? And then through that, what you can learn is what's my action effect. And then maybe that will just kind of teach the robot or the system what are the general actions that I can apply for a certain object that will have the same effect. Yeah, so that's my attempt. Do you want to attempt to answer that question yourself?
I think the nice part of being not the speaker is I can just ask all the hard questions and assume you will give me some answer. Yeah, I don't know. I think this is a hard one.
Yeah, I think that's the the classic sort of like question which we'll have to wait and see in like 30 or 40 years to see what the answer is. Maybe. Yeah. I sometimes like asking these questions in events like this, which is for there are a lot of people who are watching this at home. And do you have any advice for people who are just sort of starting out, starting their grad school career, starting their research career, joining the computer vision community or the robotics community? Like, are there things you wish you knew, or things you wish you?
Yeah, this is a great question, especially those who wants to do like robotics and vision at the same time, which I think there's a lot of interest nowadays.
Yeah, maybe I can like say a little bit about like a little bit specific for like related to robotics and vision. I think now is a really like a very special time to join vision and robotics. Why? It's because things start to work. So as I said before, like I have a vision background. So before like 5 years ago, I almost like never really worked with real robots, but actually, there's a lot of hard robotics problems that already got solved, like the controls. Actually, I don't need to code the PID control. I don't need to actually like worry about whether the voltage is a little too high. So I already has all those APIs. I have all those like good simulation environments. So maybe my advice is don't get scared or afraid. I think because there are a lot of good infrastructures out there, both for robotics learning and also for computer vision. So if you are interested, just like kind of jump in, and then this field is welcoming. Yeah.
Great, that's great. Oh, I have one more question related to this, which is like Deepak said, you're really good at formulating your problems, because I feel like once you get into the robotics space, like the space is big, right? Like you could be having lots of cameras or lots of sensors. And I really think your project really hits the nail in like a good balance of like the things you need, but then still really relatively general. Like how do you go about, when you have so much freedom about what you can assume, how do you, keep it simple?
I think sometimes the reality kind of constrains your imagination. So for example, we don't have a tactile sensor, so we don't like actually even think about that. But I think maybe one thing that like I always ask myself when I do a project is that can it work? Like can it actually work in real? But I think sometimes it may be also a limitation, because it's if you just worry too much about whether it can work now, maybe you'll start to work on problems that's relatively like approachable. But there may be also like questions that you can ask is that what if computer vision is solved and I like reinforcement is solved, what I can do, right? So I think this is a balance. Like I think like now I'm really like thinking about other spectrum. Like before I spent a lot of time to think about how to make things work. Now as I think about like if things work, what we can do next. Yeah.
Great. All right. I think that's a really good place to wrap this, unless there's other questions from the panel. Okay.
Yeah, I was just saying thank you for great answers.
Oh my God. Yes, thank you. It was
Thank you so much.
amazing. Oh, it was really great. I really enjoyed this. And thank you so much for the panelists also. This was great fun. Okay. All right. So then thank you so much.